Yesterday we talked about the curl of a vector field, and today we're going to conclude the section 13.5 by talking about the divergence of a vector field. So first we're going to want to be able to define what that term means, the divergence of a vector field. Next, we're going to want to be able to interpret the divergence, give a real-world interpretation of divergence in the context of a flowing fluid. And 3, we're going to calculate the divergence of a vector field from the vector field's equation. Alright, let's go ahead and get started. So, definition. We have a vector field f, function of x, y, and z. The output coordinates are called, as usual, p, q, and r. And we have this symbol nabla back again, representing the same thing that it did yesterday, partial in the x component, partial y in the y component, and partial z in the z component. The divergence of the vector field f is given by the following formula, and it's written div f for short. Div f can be found by taking the dot product of nabla with the vector field. Now, in other words, we can find the dot product by taking the x-coordinate of the vector field and the x-coordinate of nabla and multiplying them together, giving you partial p, partial x, and then adding partial q, partial y, and then adding partial r, partial z. So in each case, there is a matching behavior. P is the x-coordinate, and we're taking the x derivative. Q is the y-coordinate, and we are taking the y derivative. R is the z-component, and we are taking the z derivative. And then we're adding all of those together. So there are two things here that really make the divergence unique. First is that this is the first instance where the component of the vector field has matched the derivative that we have taken. In curl, p was always interacting with partial y or partial z, and even in 2 dimensions, we took partial p, partial y only. So this is our first time taking partial p, partial x. This divergence is also unique for the following reason. Notice that div f produces a scalar. Div f produces a scalar. Dot products produce scalars, whereas cross products produce vectors. Since the div is in terms of the dot product, it will produce a scalar quantity and not a vector quantity. So it eats vector fields, and it produces functions. Regular multivariable functions that produce single real numbers. Now notice as well that we have now been using the symbol nabla in actually 3 different ways. We have nabla f for a function of x, y, z, which represents the gradient vector of f, or partial f, partial x, partial f, partial y, partial f, partial z. We have nabla cross a vector field, which represents the curl of the vector field. And we have nabla f dot vector field, which represents the divergence of the vector field. So this symbol nabla gets quite a bit of mileage and gets used in 3 different ways in this class. One's for the gradient, one's for curl, and one's for divergence. Now, just as a quick summary of what the divergence represents, take, for example, the velocity field of a fluid. So the vector field is telling you how fast the fluid is moving at every point and in what direction the fluid is moving. If you calculate the divergence of that velocity field, it will tell you how much overall the fluid is trying to move away from the point x, y, z. Not move in toward the point, but move away from the point and diverge from that location overall, how much is it trying to escape and avoid that point? Okay, now let's get some quick exercise and let's calculate the divergence of the following vector field. We have f of xyz equals 2xy, x squared plus 2yz, and then y squared. So let's do nabla dot product f, and then let's take the partial derivative with respect to x of 2xy, the x component, and add that to the partial derivative with respect to y of the y component, and add that to the partial derivative with respect to z of the z component. Now, all in all, partial derivative with respect to x of 2xy is simply 2y. The partial derivative with respect to y of x squared plus 2yz is simply 2z. And then finally, the partial derivative with respect to z of y squared is nothing. So in total, the divergence is equal to 2y plus 2z, a multivariable function, not a vector. Alright, now coming up, as we have stated, we're going to be using these techniques of curl and divergence to create three-dimensional equivalents to Green's theorem. But the first thing that we need to do is show why we might need such a theorem. And so we're going to introduce first the 3D equivalent of a line integral, which is something called a surface integral. So look forward to that.